Okay, so I want to start this lesson with a chemical reaction, and that's a pretty good place for chemistry lessons to begin because we're almost always dealing with reactions. But the one I want to start with is that of nitric oxide with hydrogen gas. So I'll start with nitric oxide. I have NO, and this is going to be in the gaseous state. And then to that, I want to react hydrogen gas. So we've got hydrogen gas, and that's a diatomic element, so it's H2, and then those are going to form two things. They're going to form nitrogen gas, and nitrogen gas is also diatomic, so I've got a subscript of 2, and it's going to form water vapor. So I've got H2O in the gaseous state, water vapor. And before I keep going, I should probably balance this reaction so that we get the correct stoichiometry. And so I need to put a 2 in front of this nitrogen because we're going to end up with 2 nitrogens over here. So I've got a 2 there. And so with that, I'll have 2 oxygens. So I need a 2 over here as well. And now I've got 4 hydrogens on my right side, so I need to add a 2 in front of this hydrogen gas, and so that gives me the correct balanced formula for this reaction. I've got 2 moles of nitric oxide in the gaseous state and 2 moles of hydrogen gas, and they're reacting to give me 1 mole of nitrogen gas plus 2 moles of water vapor, H2O in the gaseous state. So whenever I see a reaction like this, I kind of immediately have 2 questions. The first one is, will it happen? So kind of the first question that I ask is this reaction going to happen? Or in other words, is it spontaneous? And a study of thermochemistry is going to answer that for me. A study of the energy levels and how favorable a reaction is to occur. The second big question that I have is, how is this reaction going to happen? If it's going to happen, how does that occur? And that question encompasses ideas like, what is the mechanism of this reaction? And by mechanism, I'm including things like, what steps does this reaction undergo as the reactants are forming the products? And then the other big part of this how is a question of the rate. How fast does this reaction occur? So I'm questioning the rate. And just like the first question was answered by a study of the thermochemistry, the second question is answered by an area of chemistry called chemical kinetics. So chemical kinetics. And the area of chemical kinetics that I want to talk about in this video is the rate. And the rate is going to answer for us how quickly do all these little reactants, the nitric oxide and the H2, how quickly are they going to collide, to form the products. And when you think about all of the chemical reactions that you see in everyday life, it's pretty easy to see that these reactions occur at vastly different rates. So you've got something like rust, and as rust is forming on kind of an iron surface, that process happens quite slowly. And then you've got a chemical reaction like fire, the combustion of a match as you strike it. And that reaction is happening extremely fast. And thermochemistry tells us nothing about the rate, but chemical kinetics does. And so there's several ways that we can measure the rate of a reaction. And so you could study every single little collision of these reactants and you could measure their frequency, but this is a super ineffective way of measuring rate, because how are we supposed to quantify all of the billions of reactions happening simultaneously and in order to determine the rate? That's pretty ineffective. But there are other ways to measure rate, and maybe we could absorb some indication of the reaction speed. For example, oftentimes a color change occurs alongside a reaction, and so maybe we can measure how quickly the yellow and the blue form a green product, and that method of determining the rate becomes a little bit more effective. And so fundamentally what we're doing here when we're measuring the color change and the speed of the color change, we're measuring how quickly the concentration of the yellow and the blue reactants, how quickly that concentration goes down, and how quickly then the concentration of the green product goes up. So we're measuring the change in concentration. And so I've got a delta sign for change, and I've got some brackets here for concentration. And fundamentally, that's what we're measuring. And so one of the most effective ways to use a change in concentration to determine rate is to graph a change in concentration as a function of time, just to set it up on an axis. So let me set up a graph for us. So we've got our concentration in molarity in moles per liter on the y-axis, and we've got our time as the independent variable on our x-axis, and we'll measure that in seconds. And so just to make it easier to see the colors that we used in our reaction, I've got blue as nitric oxide and kind of an orangish yellow as our hydrogen gas, and purple as our nitrogen gas, and pinkish red as our water vapor. And so we'll start with quite a lot of our reactants. So we have a lot of nitric oxide, and we have a lot of this kind of hydrogen gas. And what we'll see as the reaction progresses forward is we'll see kind of an immediate drop in our reactants as they become products. And so we see this kind of immediate drop in our nitric oxide and an immediate drop in our hydrogen gas. And at first that happens quite quickly because there's a lot of nitric oxide and a lot of hydrogen gas to react together. But as that reaction moves forward and there's less and less of these reactions, you see kind of the rate, which is signified by the slope of this graph, you see the rate start to decrease and start to taper off. Now on the product side, immediately you see kind of a bump in our water vapor. And that's actually, it's forming at the same rate as this nitric oxide and as the hydrogen gas were disappearing. So we've got this forming at the same rate. And then our nitrogen gas increases as well, but at half the rate of the water vapor production. And I've signified that with a shallower slope or a shallower rate of the nitrogen oxide being produced. And that's happening because according to our balanced equation up here, for every 2 moles of nitric oxide reacting, 2 moles of hydrogen gas will react, and 2 moles of water vapor are produced, but only 1 mole of nitrogen gas is being produced. So it's being produced kind of at a slower rate, and that's signified on this graph with a shallower slope. So in other words, the rate of our nitric oxide consumption is equal to the rate of our hydrogen gas consumption, which is equal to the rate of the water vapor production, and that's 2 times, all of those are 2 times the rate of the nitrogen gas production. And we can write this as an equation, and that's kind of how you're going to see it written in a lot of chemistry books. And so you see the negative change in nitric oxide divided by the change in time. So that rate of consumption is equal to the negative change in hydrogen gas consumption over the change in time. So the rate of that consumption, and that's equal to the change in concentration of our water vapor over time, so the rate of production, and it's equal to the change in concentration of our nitrogen gas over time. So the rate of our nitrogen gas production, that's a positive value. And so that's equal to the change in concentration of our nitrogen gas over time. So the rate of that multiplied by 2, because it's equal to 2 times the production of our nitrogen gas. And we can get rid of this 2 by multiplying all of these rates by 1/2. So multiplied by 1/2 and multiplied by 1/2 and multiplied by 1/2, and then when we multiply our nitrogen term by 1/2, the 2 originally that we were multiplying with canceled. And it looks a little bit confusing this way, but the reason I went through all those steps is to show you kind of generically how you'll see this written in a chemistry textbook. So let me write it out kind of in the generic form. And so kind of that generic reaction that you see a lot written is little a moles of big A plus little b moles of big B. Those are our reactants, forming this lowercase c moles of our C product plus lowercase d moles of our D product. And if we were to write the rate like we did above generically, you would see it written like this. You would see that the negative 1 over A, so negative 1 over our moles of A times the change in concentration of A over the change in time, so the rate of that consumption is equal to negative 1 over little b times the change in concentration of our B reactant over time. And when you think about it, that looks just like it does in this top formula up here, because we started with 2 moles of nitric oxide and 2 moles of hydrogen gas, and that's and we multiplied them by 1 over 2 and 1 over 2 respectively, and then we continue that with our C value, 1 over C times the delta C over delta T, and then we have the exact same thing happening with our D value, 1 over little d times the change in concentration of our big D over the change in time. And I know that here this big white value looks extremely confusing, but I need you to see that all this is saying is the exact same thing as we did with our colors before, that the rate of the disappearance of our yellow and blue reactants is equal to the rate of our production of our green product. All this formula does is generalize that and allow for us to account for the stoichiometry of the original reaction. So this is the introduction to this idea of rate.